In this video, we're going to introduce the concept of a Taylor series. So Taylor was a mathematician, Brooke Taylor specifically, who posited the following question. Given a function, is it always possible to find a power series representation of this series at a given center? Is it always possible to find a power series representation? Now what I'm going to do is write out the first few terms of this series. So C0, C1 times x minus a, C2 times x minus a quantity squared, C3 times x minus a quantity cubed, and so forth and so on. So this is what our function f of x is equal to. Now, we did mention in the previous section that a power series will always converge at its own center. That is, if I were to plug in x equals a, we would get an infinite number of terms that all turn into 0. So first thing that I'd like to take note of is if we can find each value of c, we will be set. Now, there is a method of doing so, and the method of doing so is if we can turn any of these into a constant term by taking a certain number of derivatives and then evaluating at x equals a, then we'll be able to solve for what that thing is equal to. So let's take 0 derivatives and simply plug in a. So f of a is going to be equal to c0 plus a whole bunch of terms that become 0. So that lets me know that c0 is going to be equal to f of a. If I take one derivative, the constant term is going to go away. The linear term will become the constant term. The quadratic term will become the linear term. The cubic term will become the quadratic term, and so forth and so on. This is simply applying the power rule a whole bunch of times. Now if I plug in x equals a, I'll get that f prime of a is equal to c1. Or, let's rewrite that in the following fashion. c1 is equal to f prime of a. If I take a second derivative, once again I can go ahead using the power rule on each of these terms. What was the constant term will go away. Should see a 2 there. The linear term will become the constant term. With a second power rule, that'll be 6 times c3 times x minus a to the first power. This one will become 12 times x minus a quantity squared. The term after this would have been a 5 with a power of 4. Applying the power rule again would become a 20. I'm missing something. That should be c4. That should be c5. Man, keeping track of all these things is such a pain. Hopefully we'll start to see a pattern soon. If I plug in x equals a, I'll get that f double prime of a is equal to 2 times c2. Therefore, c2 is going to be the second derivative evaluated at a divided by 2. Now if I take a third derivative, constant term cancels out. Linear term becomes the constant term. This term, we wind up with 24a4 x minus a. This term will give us 60 c5 x minus a quantity squared, and so forth and so on. If I plug in x equals a, I'm going to get that f triple prime of a is equal to 6 times c3. Or rather, c3 is equal to f triple prime of a over 6. And let's do one more just for the sake of being thorough. For a fourth derivative, we're going to wind up with 24a to the fourth plus. This will become 120 c C5. Why am I calling it A? That's ridiculous. C4. C5 times x minus a, and so forth and so on. This lets us know that the fourth derivative evaluated at a is simply going to be this constant term, which is 24 times c4, which lends itself to c4 is equal to the fourth derivative evaluated at a divided by 24. Now, a great question to ask is, as we're solving for each of these, all of these denominators are coming from somewhere. Denominator of 1 and 2 and 6 and 24. Well, this is coming from repeated applications of the power rule, where we multiply by the initial power and then the power that's 1 below that and then 1 below that and then 1 below that, all the way until we get down to 1. Well, that's exactly the concept of a factorial. So for C1, technically, this would be divided by 1 factorial. For C2, it's divided by 2 factorial. For C3, it's divided by 3 factorial. For C4, it's divided by 4 factorial. Or, if we were to generalize this, C sub n is going to be the nth derivative of f evaluated at a divided by n factorial. This brings about the concept of a Taylor series. A Taylor series states that if you have a function and you're interested in creating a power series representation centered at x equals a, then you can do so by doing exactly what we did here. This will be the nth derivative of f evaluated at a divided by n factorial times x minus a raised to the nth power. This is called the Taylor series representation. Of a function f. A Taylor series is simply a specific kind of power series. Now, when it comes to the Taylor series, any partial sum of a Taylor series is called a Taylor polynomial. Keeping in mind that a series is essentially an infinite degree polynomial, any partial sum would be a finite sum of powers of x. Therefore, we refer to it as a Taylor polynomial. Now, with that in mind, let's talk about a Maclaurin series. To make a Maclaurin series, center it at x equals 0. That's literally his only contribution. What a guy. Unfortunately, because of our natural tendency to make the center a equals 0, Maclaurin series representations tend to be much more popular than the generic Taylor series. So unfortunately, despite the fact that Maclaurin just took all of Taylor's work and said, let's center it at a equals 0, Maclaurin series tend to be more popular. Well, congratulations, Maclaurin.